Okay, welcome to OCR, A-Level Physics 2020, Paper 1, Modelling Physics. Links to the paper and the mark scheme are in the description. And I can show this paper on screen because OCR are cool. So, multiple choice first. Number 1, athlete is running at a speed of 5 meters per second. What is a reasonable estimate for the kinetic energy of this athlete? So we know that EK is equal to half mv squared. What kind of mass are we talking for a person? Well, orders of magnitude, we're not talking 10, we're not talking 1,000, so let's just go with 100 times by 5 squared, so that's effectively 50 times 25, and that's going to give us 1,250 joules. Yes, 100 is quite heavy, maybe we should have gone with something like 50, but we would have ended up with something a bit smaller than our right answer, but of course it's in the region of about 900 joules, isn't it? So the answer is C. 2. Which pair of quantities have the same SI base units? Force and strain? No, we know that's not true because force is Newton. Strain doesn't have a unit because it's just a ratio of change in length compared to original length. Force and stress, again, Newtons, but then stress is force divided by area, so we know we can't be that, can it either? So that's wrong. Pressure and stress, yes, that's sounding about right because we know that stress is force divided by area and so is pressure. So our answer must be C. Let's just check D. Upthrust is a force, so that's basically the same thing as A, so that's incorrect. Number 3, tennis ball is hit with a racket. Force applied is F. Ball has a vertical path through the air. What is correct when the ball is at its maximum height? So when it's there, the ball has a downwards acceleration. Yeah, we know that's true, so it has to be A. Let's just check the other ones. The force acting on the ball is F. No, because that was just the force that it was hit up with to begin with. We know that there's a force of mg pulling downwards at all times. The ball experiences greatest drag. No, it's got no drag at the top, does it? Because it's stopped moving and the weight of the ball is equal to the drag. No, because if that were true, then we'd have terminal velocity because the forces would be balanced. That's not true. Okay, question 4. Okay, we have this oscillating setup. We have resonance at this point here. Damping on the oscillator is now decreased, okay? Which of the following statements are true? 1, the amplitude of the oscillations at any frequency decreases. No, they're going to increase, aren't they? The maximum amplitude occurs at a lower frequency. No, that's not true either. The peak on the graph becomes thinner. Yes, that is going to be true. We're going to have greater amplitude and also the peak is going to be higher and thinner as well. So the answer is C. 5, the gravitational force between objects is that the mass of X increases and the distance between X and Y is halved. So we can say that R goes to R over T. Which statement about the new gravitational force is true? So we know Newton's law of gravitation is this. And so if R halves, then that means this goes down to a quarter. So that means the whole thing then goes up by a factor of 4 because it's on the bottom. And we know that one of the masses is increasing as well. And so F has to go up by greater than a factor of 4. And so therefore the answer is going to be B. It's times by 4 because we have that half distance, but it's getting even bigger because of that bigger mass as well. We know they're not going to be equal. A, we can see that no, it's not going to be smaller. And again, it's got to be bigger than 4F. So there we go. Our answer is B. 6, energy levels. What's the wavelength of the photon emitted? Change in energy is going to be 5.44, take away 1.36. That's going to give us our difference in energy. Now, you might have gotten caught out with this, like I nearly did. Quite often when we see times 10 to the minus 19, we just assume that it's electron volts, and I almost fell into that trap. But no, it's just times 10 to the minus 19. So that's going to give us 4.08 times 10 to the minus 19 joules. We know energy of photon is equal to HF, or in our case, hc over lambda, because we're looking for the wavelength. So rearranging that, swapping over energy and wavelength, we end up with hc over E. So that's going to be Planck's constant times the speed of light divided by change in energy. Could tidy up the powers of 10, but I can't be bothered. And we end up with 4.88 times 10 to the minus 7. In other words, 488 nanometers. So our answer is C. 7, recent analysis of the data collected from Hubble, blah, 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 blah. What is this value in seconds to the minus 1? We need to convert this then. So kilometers to meters, we times by 1,000. And then megaparsecs to meters. Well, parsecs to meters, we times by, according to our formula sheet, 3.08 times 10 to the 16 meters. So therefore, if it's megaparsecs, that means we need to times by another times 10 to the 6. So that's going to be 22. But because it's per megaparsecs to essentially per meter, we need to instead divide. It's the opposite. So we need to take our 73.5, times it by 1,000, then divide by 3.08 times 10 to the 22. Actually, what I can do is pop that all in one go, actually. But I'll write it down in full anyway. So let's just end up being 19 on the bottom there. And that gives us 2.4 times 10 to the minus 18 seconds to the minus 1. So our answer is B. So in that case, just worth remembering that if we're converting units that are just by themselves, kilometers to meters, then obviously we want a bigger number, so times by 1,000. Megaparsecs to meter, again, we want a bigger number because there's lots of meters in a megaparsec, but because it's to the minus 1, we need to do the opposite. 8, we have a wooden block on a ramp. It's stationary. The diagram is not drawn to scale, fine. So which triangle of forces diagram is correct? Well, we know that they must add up to 0 ultimately if it's not moving. So if it's not moving, then that means there must be frictional force pulling back upwards. I mean, we're told that anyway, there's a frictional force of F. So that's it right there. So there's going to be a right angle between our normal force and our friction. So let's have a look at these. Which one is correct? Well, the top one here, no, the force is going down the ramp, has to be going up the ramp, doesn't it? So this is correct, and the normal force, yeah, this looks about right. They're making a triangle, all going in the same direction, so I think the answer must be B. Let's just check the other ones. Oh, the other ones are nonsense, aren't they? Friction going down like that, and then we have friction going up. No, that's a really easy one there. It has to be B, doesn't it? 9, laser light, 640 nanometers is incident, and we have our, okay, that's nice. They've given us our grating spacing. What's the total number of bright spots that can be observed in the diffraction pattern? Okay, so let's look for the maximum order first of all. So when we have maximum order, we have n lambda equals d sine theta. So to figure this out, we need to figure out what order do we get at 90 degrees. And so we change theta to 90, sine 90 is 1, so therefore n is going to be equal to d over lambda. So that's going to be 3.3 times 10 to the minus 6 divided by, let's say, 6.4 times 10 to the minus 7. And so this just ends up being 33 divided by 6.4 ultimately. So we end up with 5.1 whatever, we don't care. The max order that we can have is 5, so we have a 5th order there. 4, 3, 2, 1, and then we have the 0th order as well. So it's going to be 5 either side plus the central maximum as well. So we're going to end up with 11. So the answer has to be D. 10, spring is stretched, blah, blah. What's the relationship between the elastic potential energy and the mass M? So we know energy stored in a spring is half Fx. We can also replace F with Kx, so we end up with half Kx squared. And so we can say, yes, when the mass goes up, that means that the force goes up as well. But not only that, X goes up as well. So we can either think about it in terms of both of these going up, or we can look at this version instead. We can say that because F equals Kx, that means that if the force goes up, that means that X goes up. So we have X squared. So that means that E should be proportional to M squared. Alternatively, we could replace X instead of F. We have X is equal to F over K. And so if we pop this in here, we end up with E is equal to a half F squared divided by K. And so we can say, well, if F is proportional to the mass, then therefore it's F squared. Either way, you're going to end up with M squared energy being proportional to, so the answer is D. In astronomy distances, which one of these is the largest? Okay, let's do it in just orders of magnitude. We have times 10 to the 16 here. What's a parsec? 1 parsec is times, oh, okay, we do have to be a bit more precise than this then. So 1.9 parsec, if we times that by number of meters in a parsec, we're timesing by, like we saw earlier, 3.08 times 10 to the 16. And so I do believe we're going to end up with more than that 4.22. No need to do the times 10 to the 16 here. So we end up with 5.88 times 10 to the 16. So A can't be right. Let's check C. Light years, they are a little bit smaller. They are, well, let's find that out. 3.42 times 9.46 times 10 to the 15. That's in the formula sheet. pretty close, to be honest. So 3.234 rather, times 10 to the 16 meters. Again, that's smaller. And AUs, we know they're really quite small. And so they're times 10 to the 11. And so if we're times it by 593, that's still only times 10 to whatever. We know that's going to be around times 10 to the, well, let's say 1, 2, 3 on top. So that's going to be 14. So it's going to be a lot smaller. So our answer is B, but not by a huge amount. 12 oscillator is doing SHM. What's the graph of kinetic energy against displacement? Well, we know that at equilibrium, we know we have the max KE, don't we? A can't be right. That's just nonsense. B is looking pretty good. So I think that's probably going to be our answer, because at amplitude, there's no velocity, so therefore no kinetic energy. C is the opposite. And then D, well, it can't just be this straight line, can it? 13, young modulus can be determined with this nonsense here. And what is the percentage uncertainty in the calculated value of E? Okay, so we have our equation. We don't care about the 4. So I'm just going to say E is proportional to F over epsilon D squared, because pi is a constant as well. So therefore I can say that the percentage uncertainty for F is 5.3. And then we have for epsilon 1.2, and for D squared we have effectively 2, because it's D squared. So 5.3 plus 1.2 plus 2, and so that's going to give us 8.5%. And so the answer is D. 14, whoa. Which one travels the greatest distance between T0 and TT? Well, it's the one with the greatest area, isn't it? Because we know area under the graph is equal to the distance, and so surely it has to be C, because this is the one with the massive distance, isn't it? C it is. Number 15. Kinetic theory is used to describe the model of particles. Which of the following assumptions is not correct? So we know we have our RAVED acronym: random, attraction, volume, as in there is none. E, elastic collisions and deduration. Okay, A, the collisions of particles with each other in the container of the walls are perfectly inelastic. Whoa. It would be true if it was elastic, because that's our E there. So it turns out that A has to be our right answer, right? Let's just check the other ones. B, electrostatic forces are negligible. Yeah, there's no attraction. Fine, so that's all to do with our attraction, our A. C, the particles occupy negligible volume. V, that is correct. There are a large number of particles in random motion. Yes, they're random, and so therefore A is the only one that isn't correct. Moving on then, question 16. We have this truck. Things on a ramp, fine. We have a theta of 10 degrees. We have a mass of a car of 1100 kilograms. We have our vertical distance. Right, so here are the forces acting on the car traveling up the slope. Complete the free body diagram for the car and label the missing forces. Okay, so the one thing we don't have, of course, is weight, isn't it? So we're going to have mg pulling down here, or you can call that weight. We have frictional force pulling down there, yes, but then of course we are going to have the force of the truck. So let's say, I don't know, pull, whatever you want to call it. And I have done the pull force ever so slightly bigger than the frictional force, because some of that mg is pulling down the slope, so the pull does need to be bigger than just the frictional force, of course. B, show the component of the weight of the car is about that. We know this, don't we? We know it's equal to mg sine theta. So it's going to be 1100 times 9.81 times the sine of 10 degrees. And so we end up with 1870 to 2 sig figs anyway, newtons. C, the total frictional force is 300. Calculate the force provided by the tow bar on the car. Well, that's nice and easy then, isn't it? Because we know we have that 300 pulling down due to the friction, and we also have the 1870. So therefore, all we need to do is add those up, because the force going up the ramp, pulling it, needs to balance those. And so we're going to end up with 2170 newtons. Of course, if you use 1900 newtons, you'll end up with 2200 newtons, 2200. D, calculate the work done by the force provided by the tow bar as the car travels from A to B. This is where our vertical distance comes in here. So I haven't drawn the whole ramp, but there's A to B. So there we go. We have 10 degrees there. We're going up the ramp all the way there. We know that force times distance is equal to work done. Just going to put energy there. What was the vertical distance again? 120 meters. That's a long ramp, isn't it? Whatever. So that's 120 meters. So we're looking for the distance up the ramp. So we're going to use, well, we have our hypotenuse and we have our opposite. So therefore we're going to use sine. Sine of 10 is equal to the opposite, 120 divided by the hypotenuse. So swap those around. Therefore the hypotenuse, the distance, let's just call it, is equal to 120 divided by sine 10. And that gives us a distance of 691 meters. Fine. So we have our distance. Now we need the force. We've got that from earlier. It's our 2,170 newtons, because in order to pull something up at a constant speed, you need to be putting in just as much force. We know that, we just answered that, fine. So therefore this is going to be equal to that 2,170 times 691. And that gives us pretty much bang on 1.5 times 10 to the 6 joules. Steel tow bar, we have a length of that, we have a diameter of that, so we know we're going to find our area from that. We have a Young modulus here. Calculate the extension of the tow bar. So we have the force as well, don't we? You'll get the mark whether you use your value or the 2200 newtons. So Young modulus equation is FL over A delta L. Let's find the area first. Seeing that there's 3 marks, let's pick up a mark, even if we get the final answer wrong. Pi r squared, or pi d squared over 4. So it's equal to pi times, oh, do I really need, okay, let's just call it 0.012 squared divided by 4. So that gives us an area of 1.13 times 10 to the minus 4 meters squared. Fine, and then we need to pop that in, but we are looking for delta L, so let's swap around delta L and E. Let's write it out just in full, just so there's no ambiguity. So 2,170 newtons times the length of 0.5 divided by the area, which is 1.13 times 10 minus 4, times Young modulus 2 times 10 to the 11. I think I'll cancel these out. Minus 4 and 11, so that just ends up being 7 on the bottom there. And that gives us 4.8 times 10 to the minus 5 meters. 17, we're heating water. Before switching on, metal heater and the water are both at room temperature. Describe the motion of the atoms of the metal heater and of the water molecules. Okay, what a weird question. So metal atoms vibrate about fixed point. In other words, they don't move, whereas water molecules move about randomly. What else can we say? If they're at the same temperature, we know that EK is equal to 3/2 kT. So that means if they have the same temperature, they must also have the same KE, or EK, whatever you want to call it. Heater is switched on. We have a power. We have the mass of the water. Let's call that MW. 10 minutes. So that's obviously going to be, let's call that 600 seconds. We have a delta T, delta theta, whatever you want to call it, of 40 degrees or 40 Kelvin. Same thing. Calculate the energy transferred from the water to the beaker and to the surroundings. Okay, so first of all, let's find out the energy going in to the whole thing. So there's going to be our power of 200 watts at 200 joules per second, times that by 600. So it's going to give us a total energy of 1.2 times 10 to the 5 joules. Now, what's interesting is that they haven't given us the SHC of the metal heater. That is something that you do really have to take into account in reality. So I'm surprised they haven't given us that. So we're going to assume that it doesn't factor into this situation. Yeah, a little bit daft if you ask me, but whatever. So energy of the water, we're going to use MC delta T or delta theta. I know delta T, so 500 grams, we're going to say 0.5 kilograms, that is, times that by the SHC 4,200, times that by our temperature change of 40. I don't think I need a calculator to do this, do I? So basically 4,200 times 20, so it's going to end up being 8.4 times 10 to the 4 joules. Okay, so we had this much going in, but the water has only gained this much, and so therefore we can say that the energy lost is equal to 1.2 times 10 to the 5, take away, well, 0.8, let's say 0.84 actually, times 10 to the 5. And so that leaves us with 0.36 times 10 to the 5 joules, or in other words, 3.6 times 10 to the 4 joules. Okay, B, okay, we have a heater in crushed ice. Oh, let's say complicated. Both funnels are identical and have the same crushed ice. Current is 5 amps and the PD is 12 volts. Okay, describe and explain the shape of the two graphs and use them to determine the specific latent heat of fusion of ice. Okay, so we can see from our graphs up here that mass is proportional to the time. So the change in mass is proportional to time. The mass of ice melted, that is. What can we see from the two graphs? Gradient is greater with heater, therefore melts at faster rate, as the gradient is equal to delta n divided by t. Change in time, whatever. If there's a constant gradient, that means that energy supplied at constant rate in both cases. What else can we say? Well, I mean, 17.2 ice gains energy from surroundings. But here's the thing, is that 17.1 ice gains the energy from heater and surroundings, not just the heater, of course. Okay, so therefore we need to find the amount of energy that's going into both. There's a couple of ways that you can do this. You can find the gradient, but actually the easiest thing is just to find out the total energy that's going in. So we know that energy is equal to power times time. So the power is going to be V times I, so that's 5 times 12. So 5 times 12, because that's V and I. Times the time, let's go with the total time, so 4 minutes. So times by 4, but then we need to turn that into seconds as well. So 60 times 4. And so we're going to end up with 14,400 joules of energy going into the one in 17.1 due to the heater. Okay, so how much mass does that actually melt? That's the question. So obviously we're going to do E equals ml, because that's our specific latent heat equation. So L is equal to E divided by M. We have our energy, but here's the thing, is that E is the energy that is from the heater, not from the surroundings. So we need to find out the mass that's melted just by heater. And so if you got this question wrong, this could be why. So the mass that is melted, well, that's 50, where are we? 55 times 10 to the minus 3. However, we can see that from the other setup that 10 of those grams of that 55 is actually just melted due to the surroundings. So therefore, the mass of the ice melted just by the heater is going to be equal to 55, take away that 10, obviously then times 10 to the minus 3. So that's 45 times 10 to the minus 3. So let's just say 0.045 kilograms. Okay, so just finishing this off then. Therefore, L is equal to 14,400 divided by 0.045. And so that gives us 320,000 joules per kilogram, or 3.2 times 10 to the 5. Now you could have alternatively figured out that if energy is equal to ml, then dividing both sides of this by time, we end up with E divided by T, which of course is power, equals M divided by T, which is our gradient, times L. Problem is that you'd have to take one gradient away from the other then, in a similar way that we took away the masses. 18 Archer, we have various things. This looks like projectile motion and SUVAT. Let's do this. So we have a horizontal distance. We have a U of 68. That is at an angle. First thing we're going to do, of course, is find out 68 cos 11. If you don't know where I'm getting that cos 11 from, then have a look at my easy vectors trick video. And that gives us 60. Let's go to 3 sig figs. Yeah, I think so. For now, anyway. So 66.8. Very similar because it's such a shallow angle, isn't it? Of course, we're going to have to find the vertical U as well, and that is 12 point. Do you know what? That's 13.0 actually. There we go. Describe how the kinetic energy of the arrow changes during its journey from when it's fired until it reaches its maximum height. So max KE at start, as vertical velocity is at max. We can say horizontal velocity is constant. At apex, V vertical is equal to 0. Therefore, KE is at minimum. We could also say that we have the max KE again at the end of the arrow's flight as well. B, show that the time taken for the arrow to reach its maximum height is about 1.3 seconds. Fine, so we have SUVAT. So we don't really care about the distance right now. We know that U is, what did we say it was? 13, we already did that. We know that V is 0. A is, okay, A is minus 9.8 meters per second squared. People get in a real tizzy when it comes to this. Sometimes it's important to keep track of our minuses, sometimes it's not. and we're looking for time. Therefore, we're going to use v equals u plus at. But at the end of the day, everything comes out in the wash anyway in this situation. The only time that you really need to be concerned with minuses and pluses is when you have something that is going up and coming back down, when it's changing direction. That's when it's important. Not so in this case. So we can say time is equal to, well, if we know that v is 0, then we can just say it's going to be u divided by a. Yes, it's going to be minus u divided by a, but we know that a is minus anyway, so that's why I say it's not too important in this situation. So we can just do 13 divided by 9.8, and hopefully we'll end up with something like 1.3, and we do. We end up with 1.32 seconds. C, the arrow misses the target, fat L. Calculate the horizontal distance measured along the baseline by which the arrow misses the target. Okay, so we need the time that it's in the air for then, don't we? So we can say, well, we just found the time, didn't we, to get to the apex, and so therefore to come back down it's going to be 1.3 plus, let's say 1.32. So therefore the total time is going to be 2.64 seconds. This is horizontal now. We're concerned with the horizontal, so we don't need suvat for this. So we can just say v is equal to distance over time. Speed is equal to distance over time for horizontal, of course. No acceleration because there's no air resistance, we're assuming anyway. And so therefore, distance is equal to v times t. So that's going to be, what did we say? 68 cos 11, 66.8 times the 2.64. Whoa, is it going way past it? So 176 meters. That can't be right. It is. Wowzers. Okay, so we literally shot it twice as far as it was supposed to. What an absolute muppet. So we're being asked to calculate how far it misses it by, so take away 90, and we are left with 86 meters. If you use 1.3, double that, 2.6, you end up with a slightly different answer of something like 84. Okay, the arrow is now fired horizontally at that speed, sticks to the target. What is meant by an inelastic collision? A collision in which total kinetic energy, not just kinetic energy, we need to say total kinetic energy, is not conserved. Easy peasy. Target is mounted on wheels. Target is blah, 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 blah. Using your distance and momentum, explain the velocity of the target immediately after the arrow sticks to the target. So we can say that total momentum is conserved. That's the first thing we write down. People quite often just miss the obvious marks because they don't think about it, because they think, oh, surely they don't want me to say that. Yes, they do. Total momentum is conserved. Therefore, mass of the arrow times the speed of the arrow is then going to be equal to the mass of the target. Okay, we should probably add on the mass of the arrow as well because it's now stuck in it, times the speed of the arrow and the target together afterwards. There we go. We can just say v of the target there. Right, so as target is heavier or has a larger mass, its speed will be much less than that of arrow to begin with. 19. Student makes a pendulum using the length of string. We have a height. The height is given by this equation here. Okay. Describe how to perform an experiment to test the validity of this equation and how the data can be analyzed. Okay, so we're being asked to prove this with an experiment. Okay. So the first thing we're going to say is we're going to release Bob from a height h, capital H that is. We say with no force applied. Yes, of course, gravity, but we want to make sure that we're not pushing it or anything. We've said height h. How are we going to measure this? Well, we can say h is measured using, well, it can either be the top or the bottom or the middle of the bob. It doesn't actually matter. But because we've got slightly different masses, we should say using center of bob. We should say from center of bob. Let's go with that. Using ruler, could have a set square as well. Card, made out of card, whatever, just so it's lined up best with our table, let's say to ensure perpendicular to surface. Actually, it's going to be very hard to get the height on the other side, isn't it? And so how do we measure h? We'll probably measure h with ruler, or we could say with fixed ruler. We could say use slow motion camera or high speed video camera to obtain an accurate value. So we've measured our h's. How do we measure m? Measure m and m using top hand balance, just a balance, whatever you want to call it. or whatever you want to call it there. We can't call it a scales. And we're going to repeat experiment for different values of h. We want a graphical method of finding this out then after we have our different results. So draw a graph of h against capital H. Gradient should be equal to, well, if we put h over the other side, we have h divided by capital H, so therefore that's our gradient. So it should be then equal to the mass over the two masses all squared. And it should be a straight line graph, shouldn't it? That's about it. 20, small object of mass m is on a thingy. Okay, so we're dealing with circular motion. Frequency of rotation is slowly increasing in area until the object slips off. Friction is equal to the centripetal force. Friction is given by F equals kmg, where k is a constant induced acceleration of free fall. K has no unit. Show the frequency at which the object slips off is given by that. Okay, so we know that F is equal to mv squared over r. But if we're dealing with spinning things, you know, rotational speeds, we should probably say that F is instead equal to m omega squared r. We're told that F is equal to kmg, so we're going to say kmg is equal to m omega squared r. M's cancel. And so then all we have to do, our answer is given in terms of pi, so we need to pop pi in there instead. So kg is equal to 2 pi f all squared r, and so that means that we have kg is equal to 4 pi squared f squared r. We just want f squared by itself, so therefore we want to get rid of everything else to the other side underneath there, so we end up with 4 pi squared r on the bottom there. Don't ask me why they've taken out 1 over the other side. I guess just because everything else is a constant, so therefore they've just separated out the radius from the constants. There we go. That is our final expression for f squared. Student plots log of f against log of r. Okay, cool. For this graph, the y-intercept is that. Use a graph to determine the constant k. Write your answer to 2 sig figs. Now we could calculate the y-intercept using the gradient and a couple of values, but to be honest, we're not too far away. I mean, they've given us a line of best fit already, so it's not even the case that we have to draw a line of best fit. We just carry this on going down here. Of course, you're going to use a ruler. So you'll end up with a y-intercept of 0.45. So we know that that is equal to this half times the log of gk over 4 pi squared. What's interesting is that OCR like LG, AQA like LOG, but they are interchangeable. But of course, this is a minus, so we do need to be careful here, because when you're dealing with logs, pluses and minuses make a world of difference. So therefore, we can say that doubling both sides, we end up with minus 0.9 is equal to the log of gk over 4 pi squared. So rearranging this, we want to delog both sides. Log, this is base 10, it's not natural log, so we can say 10 to the power of minus 0.9 is equal to gk over 4 pi squared. Therefore, taking everything over to the other side apart from k, we end up with k is equal to 4 pi squared times 10 to the minus 0.9 divided by g, so 9.8, isn't it? And we end up with 0.507, but we're being asked to give it to 2 sig figs, and so that's going to be 0.51. A kiln is used to harden ceramics. We have a cube size that are 0.46 meters long. Chamber is sealed, full of argon. It behaves like an ideal gas, so we know we're going to have to use PV equals nRT here, surely. Kiln is initially at 20 degrees. Let's turn that into Kelvin, I think, seeing that we're dealing with gases. So we add on 273, so that gives us 293 Kelvin. So that's our T. We have a pressure of 100 kilopascals. Calculate the amount of argon N in the chamber in moles. Lovely. So we know that the volume is going to be 0.46 cubed. And so that gives us 0.0973 meters cubed. So we're looking for N. That's equal to PV over RT. So that is 100 kilopascals. So 1 times 10 to the 5 times, tell you what, let's convert that then, 9.73 times 10 to the minus 2. So tell you what, actually I can just change that to times 10 to 3, cool. Divided by 8.31 times our temperature of that. And we end up with, well, 3.996. So basically 4 moles. Temperature of the kiln is increased to, whoa, 1300 degrees. Yowzers. Calculate the pressure at 1300 degrees Celsius. Okay, so we first of all need to figure out what's staying constant in our equation. N is staying constant, R is staying constant, and also V is staying constant. So therefore we can say that P1 over T1 equals P2 over T2. We're looking for this. So therefore the pressure afterwards is going to be equal to pressure before times the ratio of the temperatures. So that was 1 times 10 to the 5 times our second temperature. Well, that's 1300 plus another 273. So that's going to be 1573 divided by our 293. And, well, just doing the ratio, that gives us 5.4. And then times that by times 10 to the 5. So that's our new pressure. We know that P is proportional to T in this case, and so therefore the temperature has gone up by 5.4 times. Therefore the pressure has 2, because we've been given a nice number for the pressure to begin with, which it is. Temperature of the kiln is 1300. A single atom of argon is traveling horizontally towards the chamber. We have an initial speed of 990 meters per second. After collision, we're looking at momentum. So we know that it's bouncing off the wall and coming back. So therefore we know change in momentum is going to be m delta v. And so because it's going forward at u and then coming back at minus u, that means that this is equal to 2 lots of mu, or m times 2u, same thing. So that's going to be 2 times 6.6 times 10 to the minus 26 times speed of 990. And that gives us 1.3 times 10 to the minus 22 kilogram meters per second. That's our impulse of the atom. Assume that this atom does not collide with any other argons. It travels horizontally, making repeated collisions with the opposite vertical walls. Show the atom makes about 1,000 collisions with side X in a time interval of 1 second. Okay, so we saw that the distance was with side X. Okay, so the distance is actually 2 lots of 0.46, because so there's our kiln, and so they're saying it's going there and coming back. You could also just do half the time, whatever, it doesn't matter. So we end up with a distance there and back of 0.92 meters. Okay, and we're looking for, I know the speed is 990 meters per second. So that's okay. We have meters and we have meters per second, units are your friends. If we do one divided by the other, then we're going to end up with just seconds to the minus 1. And that is what we're looking for. We're looking for collisions per second. So therefore, we're going to do 990 divided by 0.92. And we end up with 1,076 collisions. Calculate the average force on side X made by the atom. So we're looking for force. We have the momentum from above there, the change in momentum. Delta P is 1.3 times 10 to the minus 22 kilogram meters per second. Tell you what, let's just say Newton second. Actually, we know that's the alternative unit for momentum. And so therefore we know that force is equal to rate of change in momentum. So there's delta P over time. So we have a change in momentum, but what's the time going to be? Well, if it does 1,000 collisions in 1 second, then that means that the time is going to be 1 over 1,000. So there we go. So we can replace this with 1 over 1,000. So actually what this ends up just being is delta P times 1,000, because it just flips to the top there. So that just ends up being our 1.3, but now it's going to be times 10 to the minus 19 instead. With that calculation, explain how your answer could be used to estimate the total pressure exerted by the atoms in the kiln. All we have to do is multiply by number of argon atoms in the kiln to get total force on X. We're not being asked about the force, we're being asked about the pressure. Pressure, therefore, is then equal to force divided by area. 22, long wooden cylinder, upthrust. State Archimedes' principle. Upthrust on an object is equal to the weight of fluid it displaces. Pressure exerted by the liquid alone is that. Calculate the density of the liquid. So our classic equation, pressure is equal to H rho G. Therefore, rho is equal to P over Hg. So that is 1.9 times 10 to the 3, 1,900, whatever, divided by the height, which is 15 centimeters. We're told that above there. So meters 0.15 times 9.8. And we end up with 1,293 kilograms per meter cubed. So let's just round that to 2 sig figs, 1,300. B, the cylinder is pushed down as a liquid and then allowed to oscillate freely. The graph of displacement. Oh, this is cool. It's upthrust and SHM. Sweet. Cylinder oscillates with a frequency of that. And we have an amplitude of 2 centimeters. Calculate the displacement at time. T equals 0.6 seconds. Okay, so we're going to need our OG SHM equation that tells us what the position is, the displacement is at any time. X is equal to A sine omega t. Hang on a minute. Oh, no, we're not using sine because it's starting at amplitude. Guys, just to remind you, cos and sine, they're exactly the same function. It's just one is shifted 90 degrees from the other one. So you just have to use the right one for the right situation. So just be careful. If it says in your equation sheet, use sine, you might have to use cos instead, depending on the context. So this is equal to, what do we say? We're giving it in centimeters, so that's fine. So we'll just say 2 centimeters times cos. We know that omega, of course, is 2 pi f. So let's just write that down. So this ends up being 2 pi ft. So 2 pi times, what was it, 1.4 hertz times 0.6 seconds. And you must make sure that you're in radian mode here, because if any of your cos and sines have pi's in, you must be in radians. And we end up with 1.07 centimeters, so 2 sig figs, 1.1. Calculating the maximum speed of the oscillating cylinder, Vmax, is equal to 2 pi Fa, or omega A. So 2 pi times 1.4 times our amplitude. We are looking for meters per second, so we do need to change our amplitude to 0.022 centimeters. Okay, so we should end up with 0.176, so 0.18 meters per second. Cylinder is now pushed down further into liquid before being released, as before the cylinder oscillates with simple harmonic motion. State the effect this has on the amplitude. It's increased. Time period, unchanged, because we know that amplitude, whether it's to do with springs or pendulums or anything, amplitude does not affect frequency or time period. 23, Hayabusa 2, Ryu Hayabusa, arrived at an asteroid called Ryugu. The asteroid orbits the sun in an elliptical orbit. The diagram is not drawn to scale. You don't say. Indicate with a letter X on the orbit where the asteroid would be moving at a maximum speed. Of course, it would be when it's closest to the sun. Use Kepler's law to explain your answer. Kepler's second law is all to do with segments. And if we draw segments that are joining the asteroid on the sun over the same time interval, the orbit is going to sweep out the same area. So we're going to have equal area. Therefore, closer to the sun, distance traveled is going to be greater because we have a wider segment. So therefore, we have a greater speed. So define gravitational potential. Nice and easy. You should have this locked and loaded. It is the work done to move unit mass. We don't say per kilogram. We don't give a unit in definitions. We always say the unit, whatever. Unit mass from infinity to that point. It's not the other way around, because all of our values are negative, because we know work needs to be done to move something to infinity. But that's our definition for potential. So the magnitude of the gradient is equal to gm. So our equation is V is equal to minus gm over r. We know that 1 over r, so therefore we can just say V is equal to gm times minus 1 over r. So therefore V over minus 1 over r is equal to gm. That's it. Use a gradient of the graph to show the mass m of the asteroid is about that many kilograms. Right. So let's have a look at our graph. Let's get a gradient then, shall we? So we have 7 here. 7 times 10 to the minus 2, those. And here we have, what's that, 2.1, 2.2, 2.3 times 10 to the minus 3. So the gradient is equal to 7 times 10 to the minus 2 divided by 2.3 times 10 to the minus 3. Or in other words, 70 divided by 2.3. And we end up with, well, it is minus, but we don't really care. We only care about the magnitude, really. So 30.4 for the gradient. We know that that is equal to GM. We've just seen that. And so therefore, M is going to be equal to the gradient divided by G. So that is 30.4 divided by 6.67 times 10 to the minus 11. And we end up with 4.56 times 10 to the 11. So yeah, pretty much 4.6 times 10 to the 11. In 2018, probe, blah, 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 blah. It was released from rest from the spacecraft from a distance of 600 meters from the center of the asteroid. Assume the spacecraft was stationary relative to blah, blah, blah. Calculate the speed of the impact when mass got landed on the surface of the asteroid. So, you know, we have something dropping. You might be tempted to say, oh, it's half mv squared equals mgh. We know it doesn't work like that when it comes to gravitational fields. So we can still say that KE is equal to GPE, but rather we should say that KE is equal to the change in GPE. So in other words, E1 take away E2, isn't it? So let's find out the change in GPE first. So E1 take away E2. So we need to be thinking in terms of GMM over R1 take away GMM over R2. It's not getting to the center of the asteroid, is it? So we can't just say our distance is 600. And of course we can't say, well, let's see how close it is getting. The surface of the asteroid is 1 over 2.3 times 10 to the minus 3. So therefore, R2, in other words, the radius of the planet is going to be, so we end up with 435 meters. Cool. The difference in distance is 165, but we can't put that into our equation because our R1 and R2, they have to be from the center of the asteroid. So therefore, we can factorize this, of course. We can say that's GM. I'm making life slightly difficult for myself because, well, we've got M's that cancel. So, I mean, we could figure out the actual potential. Let's do that, actually. Let's do potential instead. So let's say V1 minus V2 is going to be GM over R1 take away GM over R2. You'll see why I'm doing this in a second. Because, yeah, we could find out the change in energy. That's fine. But just to make life slightly simpler for ourselves, of course, I can factorize this, can't I? So that's going to be 6.67 times 10 to the minus 11 times the mass. We said that was 4.6 times 10 to the 11. Oh, that's cool. Minus 11 and 11 cancel. And so times up by 1 over 435, take away 1 over 600. Going to do the brackets first. And I end up with a change in potential of 1.94 times 10 to the minus 2. And of course, that's going to be joules per kilogram, isn't it? So I have a change in potential. And so therefore, I can say that half mv squared is equal to the change in potential energy. And so I can say that's m times the change in potential. See why I did it now? Because the m's cancel. So therefore, I can say that v is equal to the square root of 2 times the change in potential. So I'm just going to, there we go, let's put that there. And so there's going to be the square root of 2 times our 1.94 times 10 to the minus 2. And we end up with a speed of 0.18 meters per second. So we go a couple of ways that you could have done that question, but it all comes down to kinetic energy equals the change in GPE, not the total GPE if it's falling to the surface. 24, our sun will eventually become a red giant. Isn't that fun? Describe and explain the next stages of evolution for our sun. So we can say less energy released due to fusion. And so then we can say that force of gravity will become greater than force resulting from gas pressure. We can say the core will collapse. What else can we say? Well, outer layers will be released as they cool and expand. We can say results in nebula. And we can say that core is left as white dwarf. We can also say fusion doesn't happen in the core anymore. Boring. Rigel is a blue giant star in the constellation of Orion. Show the surface temperature of Rigel is about that. So the first thing we can do is say that, according to Venus law, lambda T is a constant. So therefore we can say lambda 1, temperature 1 is equal to lambda 2, temperature 2. So therefore, if we're looking for just temperature of this, then we can say that it's equal to that. So therefore we're going to say it's 500 divided by 240. We don't need to be concerned with the nanometers because it's just all relative. And we know the temperature of the sun is 5,800. So we can already see that, yes, we're going to end up multiplying by a factor that is similar to that. And we end up with 12,083. So yes, that is 12,000 Kelvin. Calculate the radius of Rigel. So we can say the luminosity, according to Stefan's law, is equal to Stefan's constant times the area times the temperature to the power of 4. Of course, area for a sphere is equal to 4 pi r squared. We're looking for the radius, so therefore we can rearrange this to find r squared is equal to L over everything else. So 4 pi sigma t to the 4. And of course then, that means that we have the square root of that will give us the radius. So we have the luminosity is this here, 4.62 times 10 to the 31. Divide that by 4 pi times 5.67 times 10 to the minus 8. And times that by 1.2. Oh, let's just call that 12,000 actually. Seeing that we're having to raise it to the power of 4 anyway. So just be careful popping all these numbers in. And I end up with a radius of 5.59 times 10 to the 10 meters. So let's say that's 5.6 times 10 to the 10. See, an astronomer claims to have discovered a white dwarf with a mass twice that of our sun. Suggests why this claim must be incorrect. So the magic number here is about 1.4. White dwarfs mass must be less than or equal to 1.4 solar masses. Just something you need to remember. So there we go. That's it. Hope you found that helpful. If you did, please leave a like. And if you want to have a look at some more papers, then click on the card and it'll take you to the OCR playlist. See you next time.